Hey guys, welcome to my hopefully last video on the Lewis structures, and we're going to talk about hyperactivation. Remember, we talked about the dative bonding and the covalent bonding. Covalent bonding is what we always do to make atoms feel satisfied. So that's what I'm going to do for SF6 here. And then if we go beyond um, octet rule, you have two choices. If you have something that like oxygen that needs two electrons, we could donate a lone pair to actually make the dative bonding, or we could do hyperactivation, which happens all the time for a fullerene or something group 7 that needs only one. So sulfur group 6, it could happily share its two single reacting electrons with two fullerenes to make SF2. Okay, and the hyperactivation, there's one more story to hyperactivation. It happens for central atoms that are period 3 or more. Sulfur is period 3. It means if you're period 2, just like oxygen, you can't have OF6. The molecule doesn't actually exist. We do just have OF2. Fullerene cannot make any element that is period 2 or 1 to actually give up its lone pair to join in hyperactivated bonds. For this, what happens? We have four more fullerenes waiting to come in. They're crying actually to come in, and they're not going to accept dative bonding because fullerenes or anything group 7 only needs one electron. So they're going to attack these two lone pairs, shatter them up, and kick them into a higher shell or higher layer. That's why the central atom must be period 3 or more to be able for the fullerenes to attack its lone pair. Oxygen doesn't have another like layer or shell. So this would then be able to satisfy the hunger for two more fullerenes. Anytime you shatter a single lone pair, it would generate two single reacting electrons that would actually satisfy the hunger of two halogens or fullerenes. It's SF4 now, but we need SF6. So I would shatter the other lone pair, put it into two single reacting electrons in a outer orbital to satisfy these two fullerenes. Now I have 0 lone pair, all the lone pairs are sacrificed, and I have 6 surrounding atoms, gives me 6. That's octahedral framework, and this octahedral framework with 0 lone pair would call the geometry that is octahedral. Now remember, when we're going to draw that octahedral geometry that I'm just showing you, we first do the in plane position, okay, the equatorial, and then we do the actual top and actual bottom. Okay, let's just do that. The in-plane position, and then the actual top and actual bottom. In the middle, and like in the center, I do sulfur, and I do the fullerenes, and the fullerene on the top, the fullerene on the bottom. That's this. Now I could do this, which makes it more like a octahedral framework, but you really don't have to do this. Okay, it's fine to just draw the planar in plane position and then the actual positions. Let's do PF5. Now my PF5 phosphorus is also period 3. That's why it can do that. Nitrogen cannot give you NF5, it could only give you NF3 that we have talked about previously, and 3 of those fullerenes are going to be able to do a friendly sharing of electrons with your phosphorus. That makes the fullerenes be satisfied through their octet, and also the third one of them, when we do the third bond, that would satisfy the phosphorus, central phosphorus as well. So what I'm going to do the two remaining fullerenes, well, it doesn't accept fullerene or anything group 7 doesn't accept a dative bond because it only needs one electron, so I'm going to tag this lone pair, making it shattering up, making it two single reacting electrons. That would actually satisfy the two other fullerenes. Okay, and with this I get 0 lone pairs on my phosphorus and 1, 2, 3, 4, 5 surrounding atoms. That gives me PF5. PF5 is a trigonal pyramidal framework. The geometry is also trigonal pyramidal, trigonal bipyramidal, because it doesn't have any lone pair. And if you don't have any lone pair, the geometry won't change. It's the same name that you have. So this is trigonal bipyramidal. In the plane position, you have 3 surrounding atoms, and these are the actual ones. These are the equatorial ones, my bad. And you have 1 actual top, 1 actual bottom. That makes you the trigonal bipyramidal. You could draw it like this. Again, the in-plane positions first, and then 1 actual top, 1 actual bottom. And the P is going to be on the center. Fullerene, 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 fullerene. Again, you don't have to draw this green surrounding, and I'm not going to do it for the rest of the molecules, but just for this one, to make you understand that we have the exact same trigonal bipyramidal framework that we talked about. We just do the in-plane position and actual top and actual bottom. It would be reminiscent of the structure of a trigonal bipyramidal. That's the geometry. Okay, let's go on to XeF2. Now XeF2 is the structure that I'm going to draw here, and it has xenon, which is group 8, interestingly. Now, what is interesting about this molecule, about the central atom, it doesn't want to do any bonding. That's why we call xenon a noble gas. It doesn't want to actually share electrons through covalent bonding at all, because it is feeling happy. But with fullerene, well, xenon is period, I believe period 6, if I don't make a mistake, and fullerene is going to attack one of its lone pair, making it 2 single reacting electrons that will satisfy my 2 fullerenes. Each of them is group 7, just 1 bond satisfies their hunger. So 2, and again, each time you shatter 1 lone pair, it's going to satisfy 2 halogens. Most of the time it's fullerene. If it's other halogens, also it would, 1 lone pair would satisfy 2 of them. So this is now 3 lone pairs and 2 surrounding atoms. Again, trigonal bipyramidal framework. So again, this framework, but this time you have 3 lone pairs, okay? So if I have 3 lone pairs, and for this central moiety, I do know that the lone pairs for trigonal bipyramidal framework, this framework, the lone pairs are going to reside in the equatorial or in-plane position. It means I'm going to detach this in-plane, this in-plane, and this in-plane position to give me the structure I'm looking for. And I end up having a linear structure. Remember, I just am allowed to put my lone pairs in the in-plane positions. Okay, this means my lone pairs can be here, and it's not going to be in the corners again, just like we did before. It's going to stick to the atom. So they're going to be in trigonal bipyramidal geometries. Lone pairs go to in-plane position. In contrast, when we have octahedral, the lone pairs go to top or bottom, so the actual position. So we have 1 fullerene on the top, 1 fullerene in the bottom, and it would be a linear geometry. Okay, that's this. Let's go to XeF4. Now XeF4, again we have xenon, and xenon have 8 electrons, and 8 electrons are not going to actually be happy to react. So it still takes the fullerenes to attack the xenon itself, and they're going to shatter this to hoist in 2 of those fullerenes, just like we did with XeF2, which is a linear molecule, and it's not even XeF4, so I have to attack 1 more. Now I have 4 of those fullerenes, and I could say, okay, now I have 2 lone pairs around my central atom and 4 fullerenes. It gives me 6. Now it's octahedral geometry with 2 lone pairs. So I'm going to detach the top actual one and the bottom actual one to actually make the structure of xenon F4. It's going to be called a square planar, an octahedral geometry my bad, an octahedral framework with two line pairs, one goes down, one goes top, and then it gives you a square planar geometry. That's XEF4. Let's just try it real quick here. So again, the in-plane position goes first, and then the top axial, bottom axial. Those are the ones that we draw later on. So XE goes in the center. I'm not going to put the line pairs top on here or bottom here. I just stick them through the atom on the top and on the bottom, and I get rid of this. Okay, because line pairs doesn't have shape. That's what we detach these two. And then it goes foldering, 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 foldering. Okay, that's the structure of XEF4, a square planar geometry. Let's now talk about I3 minus. Now we do also have BR3 minus. That's going to be the exact same structure, but only instead of iodines I have to put boramides. Okay, so let's do this. Now again, I start with I minus. Iodine is group 7, so if it's I minus, it's just like xenon, reluctant to react again. And if I wanted to accommodate the two iodines that are waiting outside, I have to shatter one of these line pairs to hosting two of these halogens. Okay, now that's three line pairs around my central atom and two surrounding atoms, two iodines, to make 5. Okay, and 5 is again trigonal by a pyramidal framework, this framework. Okay, and now I have 3 line pairs. Line pairs, remember, go to the equatorial positions for this. It means I have to detach the ones that are in plane. So I detach these 3 to make to be remained with a linear geometry. So that's my geometry, a linear one. And I'm gonna draw this. Remember, when we do the Lewis structure, the charge then goes for the whole molecule. Okay, so in the center I put iodine. I know it's I minus, but because this is my final Lewis structure, or I know that the charge should go for the whole atom, so I do brackets and things. And then the line pairs should go to in plane positions. I don't put them on these corner side. I just stick them to the atom. And then one iodine on the top, one iodine in the bottom. That's the geometry that I do expect, a linear geometry. BR3 minus is going to be exact same thing. I'm just going to show you that real quick. We're not going to do it from the scratch because it's going to be the exact same process that we did for I3 minus, only replace boramide for iodine and you'll get that. We don't have Cl3 minus or F3 minus. They don't form it because the central moiety must be period 3 or more. Okay, we then move on to IF3, BRF3, and CLF3. I group 7, and I want to mention that if I do this, happily it could only host only one fullerene. So if you do just one bonding with one of the fullerenes, it would give you a satisfied not only fullerene but also central moiety. So the iodine doesn't really want to do anything more, but the fullerenes are waiting and crying outside. There are 2 fullerenes, and they are going to actually shatter one of these line pairs because fullerenes are group 7 and they cannot accept the leaf bonding. So if they shatter up one line pair, both of them could be satisfied through simple hyperactivated covalent bonding. And now I have 2 line pairs, 3 surrounding atoms. Again, gave me 5 sites or a framework that is trigonal bipyramidal, and the line pairs should go to the in-plane positions. Now for this, in my model I could detach any of those that I want. Let's just detach this. But in the paper, the way I'm going to show it to you, Let's just draw it and show you what happens in the paper. In the 2D paper, you usually draw it like this. So the best one to actually give you a good perspective of what's happening, let's put the iodine in the center. And then I have one lone pair to put, two lone pairs. The two that I'm going to use, let's just attach this one. It would give you this. The two that I'm going to use is this one and this one. Okay, if I have one lone pair, I'm going to detach to put the lone pair here. If I have two of them, I'm going to put the lone pair here. On your model, you could do any of those three, and then the way you look at it, it's just like this. It's a T-shaped molecule. Okay, so I just delete this and this, and put my lone pairs here, and then, and again, there is nothing wrong with doing other lone pairs. If you do it, I don't take it's wrong, but the geometry would be better represented. This is called a T-shaped geometry. A trigonal bipyramidal with two lone pairs, it gives you a T-shaped geometry. And if you do it like this, it would have a better resemblance to a T-shaped molecule. Okay, it's not wrong to put the folder in here and do these lone pair, two lone pairs on this and this. That doesn't make it a wrong representation. So BRF3, just put boromine here. We don't do it from scratch. It's just boromine instead of the fullerene in the center. And CLF3, the exact same story. Now we have a choline in the center. So that's BRF3, IF3, CLF3. Let's just do IF5. I'm not sure if we do have a CLF5 because CL is kind of reluctant to do this. It's period 2, so period 3, so very reluctant to do this. Okay, now iodine, again group 7, it's going to share its single reacting electrons. It fills octet. It doesn't really want to do anything more than this, but there are 4 fullerenes waiting outside to attack these lone pairs. So if they attack this one, it would satisfy the hunger of 2 of them. And if they attack this one, it would also satisfy the hunger of yet 2 more of them. So we have 1 lone pair, 5 surrounding atoms, 6, an octahedral framework with just 1 lone pair. So there's the octahedral framework. And remember, on the octahedral, the actual ones are the ones that you're going to actually look for and attach this one on the top or this one on the bottom. That doesn't really change anything to give you a square pyramidal geometry. So that's the square pyramidal geometry that you're looking at. Let me just draw it real quick here. Again, I draw the incline position first, and I have 2 actual positions. In the central part, I'll just put my iodine, and then the lone pair should go on the top or in the bottom, but I don't put it at the end of this line. I just stick it to the atom. Here I put it on the top to actually represent the shape that I have here in my depository. And you can see that just finally erase those lines to make sure that these are single bonds, not double bonds. This is a square pyramidal geometry. Again, I could do this, but it's